This next section is about gas mixtures, and I probably have to break it up into a couple of different sections. But basically, it begins with the idea that if you take a mixture of gases, it essentially behaves like a bunch of gases that are independent of each other. That is, they don't interact with each other, the molecules don't interact with each other. Their properties are essentially additive. So, for example, air is composed of 78% nitrogen molecules, 21% oxygen molecules, and 1% of argon, mostly argon, and then other gases, right? Well, because the gases occupy or act independently of each other, nitrogen really occupies 78% inside of a container. Now that 78% of the volume is dispersed throughout the container, but as a result of being 78% of the volume, it also exerts 78% of the pressure. And this is entirely dependent on the number of molecules of the gas and not really the identity that it's nitrogen, oxygen, or argon, for example. So it was actually John Dalton, the guy from atomic theory, that originally made this sort of discovery that the gases within a mixture of gases act independently of each other. And John Dalton was an interesting character. He used to walk around in the swamps around Manchester, England, and sample gases from the swamp and analyze them for their behaviors. And this is kind of how he made this discovery. So, anyways, what we know now, based on what Dalton did, and also based on the ideal gas law, is that if we have a mixture of gases, that the total pressure is just the sum of what we call the partial pressures. Now, partial pressures are just the fraction of the pressure that's or the part of the total pressure that's created by the one gas. So since, for example, air is 78% nitrogen, right? 78% of the pressure of one atmosphere, or 0.78 atmospheres, is the partial pressure of nitrogen in air. Using the ideal gas law, we can go a little bit further and we can show the following. We can substitute in the different expressions for the partial pressures of each gas based on the ideal gas law. So for A, for example, I can write the pressure of A is equal to the moles of A times RT over V. Now, a gas in its container, right, with a mixture of other gases, they're all going to be at the same temperature and occupy the same volume, the volume of the container. So I don't need to make special notations for the temperature and the volume, but that means down here I can write NA over RT over V for the pressure exerted by the gas A. And then I can do the pressure of B times RT over V. That's going to be the pressure component, for example, like the oxygen's exerting in the air. And then I can have the pressure of C. That would be NC times RT over V. And I can continue this on. This is what the ellipses means down here. This equation could go on for as many gases that are in the mixture. Now, if I take that three-component mixture and recognize that RT and V are all the same, those can be factored out, and I can be left with this. NA times NA plus NB plus NC times RT over V. So I factored out the RT over V. That's going to be equal to my total pressure, P total, like this. And I can summarize that a little bit more. I can say N total is equal to all of this. That is, if I add the moles of gases up, that's going to be equal to the total number of moles. I'm going to just call this NT. So now I have P total is equal to N total times RT over V. Now, one of the interesting concepts that falls out of this is something that we call the mole fraction of a gas. To get the mole fraction of a gas, all you have to do is recognize the following. I could take the pressure of A and divide it by the pressure total, right? And so the pressure of A is NA times RT divided by V, and the pressure total is NT times RT over V, and the R is the same, of course, because it's the constant, but the T and the V are also the same, so this ends up just being NA over NT. So this term, NA over NT, is the fraction of A in the total number of moles of the gas, so we give that a special symbol. This is a Greek letter X, the capital version. It's a chi, or the X, I think it's an X. Anyways, it's an X, looks like an X. This would be the mole fraction. And then if I put a subscript on it, like this is the mole fraction of A. And that can be gotten in one of two ways. It can be the moles of A divided by the moles total, or by equality, I can calculate it as the pressure of A over the pressure total. So here I've rewritten the relationships a little more cleanly, right? And also included a problem to show you how you would use this information. So it says that in an air mixture with a total pressure of 207 bar, so this is our scuba tank from before, what is the pressure exerted by oxygen? And it says air is 21% oxygen by volume. So how do you treat the 21%, right? And how do we use these equations? So 21% by volume means 21% of the moles are oxygen. It could have been 21% by pressure as well, and it means the same thing because the gases are all acting independently of each other. So we can interpret 21% by volume, which is the common way of saying it, as 21% of the moles. So that really is called the mole percent of the gas, and we can create it into a fraction just by dividing by 100%. And so the mole fraction of oxygen is actually 0.21. Now my total pressure is 207 bar, and so all I need to do is take the mole fraction and multiply it by the pressure. It doesn't really matter what the units are here, because whatever units you have your pressure in, that's what it'll come out for the gas. So this is going to be 0.21, and fractions don't have units because it's moles divided by moles, times 207 bar, and that'll be equal to 43.47, 2 sig figs, so we'll round it there, bar, or 43 bar like this. So that's of the 207, that's the fraction that's represented by oxygen. Most of the rest of it, right, the 78% of nitrogen, right, represents most of the rest of the pressure of the gas. So here's sort of a typical partial pressure problem, and unfortunately they're super wordy. But let's go ahead and read it and see what we can piece out of it. It says a gas mixture, so when you see that, you're thinking partial pressures, with a total pressure of 745 millimeters of mercury contains each of the following gases as indicated. Partial pressures, right? CO, 125 millimeters of mercury, argon, 214 millimeters of mercury, and O2, 187 millimeters of mercury. The mixture also contains helium gas. What is the partial pressure of helium gas? And then it continues on. What's the mass of helium in a 12-liter sample of this mixture at 273 Kelvin? So let's go ahead and sort of get into how we solve this problem. First of all, it's two problems, so don't worry about the mass, okay? The next thing to recognize is that we can write a partial pressure equation But most of you will skip this step, but I'm going to go ahead and do it. P total is 745 millimeters of mercury, right? That's going to be equal to the pressure of CO2 plus the pressure of argon plus the pressure of O2 plus the pressure of helium. That's the sort of the gist of Dalton's law of partial pressures. I have 4 gases now, right? And notice what they've done. They've given you 1, 2, 3 of these, and they're asking you for what that is. So really all you have to do is say the pressure of helium is going to be equal to, then it's 745 millimeters of mercury minus, and then you can put in the rest of these, the rest of the pressures of the gases that are given. So for example, for CO2, gosh, 125, right, millimeters of mercury. And then I guess I'll subtract them each. That's fine. That's what you'll do on your calculator. You're going to subtract 214 millimeters of mercury. Right, and you'll do this, and then what you'll get when you do that calculation is you'll get 219 millimeters of mercury. If I kept writing, I would run out of space, so you got to subtract the pressure of the oxygen as well. So there is the first answer. All you have to do to get the partial pressure of the unknown gas is either sometimes do a mole fraction, but in this case it's just straight subtract from the total. Okay. Now, what's the mass of helium gas in a 12-liter sample at 273 Kelvin, right? So this becomes an ideal gas law problem, and it's a little bit tricky to see, but you have a pressure, you have a volume, and you have a temperature. So now we can do the moles. So all you need to do is say, okay, I have my pressure, volume, temperature, right? PV, I always do PV, N, and T. It bothers me if I do it otherwise, but that's the one I'm looking for there. 273 Kelvin's given, right? So that unit's good. My pressure for helium is in millimeters of mercury, right? So that's 219 millimeters of mercury. And I'll need to convert that over as 760 millimeters of mercury is 1 atmosphere. That comes out to be 0.28816. Sorry, this is all jammed in here. Poor planning on my part. And then the volume is also okay. It's in 12.0 liters. And so now I'm going to say N is equal to PV over RT. And I can start plugging in my values. 0.28816, 3 sig figs, atmospheres, times 12.0 liters. Divided by 0.08206 liters times atmospheres per mole times Kelvin, and temperature 273 Kelvin, like that. And that'll give me 0.15435 moles of helium, 3 sig figs, and then what I'll do is I'm just going to give you the answer, but then you need to convert that over to grams, and so what you'll use is the molar mass of helium, and your mass will end up being, grams of helium will end up being 0.6178 grams with 3 sig figs, so 0.618 grams. And I ran out of space, so you can round that. That's the answer unrounded. Again, a lot of words in these partial pressure problems. Usually, at least part of it's fairly simple. And because this is the gas laws chapter, usually you have to do something with that partial pressure, like calculate the number of moles of the gas, or calculate the volume the gas occupies, things like that. So here's another kind of problem that you might see when you're dealing with partial pressures. It's one that it requires you to calculate a mole fraction based on quantities of different gases that are given. Sometimes the gases are given in moles, but sometimes they're given in grams. And so if I want to know what the pressure of helium in a mixture is, if the total pressure is 10.75, right? You need to know that the pressure, you need to recall that the pressure of helium is the pressure total times the mole fraction of helium. So in order to get the mole fraction of helium, you need to know the total number of moles of gases, right? We need to know mole total, and we need to know the moles of helium in the mixture. So these are the two things that you'll need to calculate mole fraction. I kind of went around that backwards, sorry. All right, so having said that, how do you get the moles of helium? Well, if you're given 12 grams of helium, right, N of helium is going to be 12.0 grams times, and then it's 4.003 grams for every 1 mole. And that will be 2.998 moles. 2.998 3 sig figs moles. And then you also need to know the moles total, which means you need to know the moles of methane. And methane is CH4, in case you've forgotten. So I'm going to go 98.0 grams of methane, CH4, and then I need the molar mass, which I won't bother calculating here, but the molar mass of helium is 16.04 grams for every 1 mole. Kind of depends on which periodic table you used. And then for that number, what you end up with is 6.1087. So really 3 sig figs moles like that. So my NT, is simply 2.998 moles plus 6.1087 moles. And my moles of helium is 2.998 moles. So what that gives me, this is moles down here, sorry. What that gives me for my mole fraction of helium is 0.3292. And again, no units in the mole fraction. So now to calculate the pressure of helium in the mixture, I can take the total pressure, which is 10.57 atmospheres, and then multiply it by, I could just put the number right here, 0.3292, and that gives me 3.4796 atmospheres. I have 3 sig figs, so I'm going to call it 3.48 atmospheres. So that's the pressure of the total represented by helium when you have a mixture of 12 grams of helium, right, and 98 grams of methane.